Hi, everyone. All right, what we're going to be doing today is we're going to be completing another type of model, a computer simulation, showing the relationship between wavelength, frequency, energy within electromagnetic wave. Let's start by setting up the simulation. I'm reading the directions just from your packet. It says, set up the simulation. We're going to select oscillate up here in the left-hand corner. Notice it's starting to move. We're going to select no end up here in the right-hand corner. Select no end, so it's not being held back. We're going to select timer. Timer is down here in the lower right corner, and rulers. So the rulers will be important when we are measuring the wavelength of a wave. So in part 1, it says change the frequency of the wave to 0.5 hertz. So remember, hertz is a measurement of frequency, how frequently a wave passes a given point in 1 second. So we are going to decrease this down to 0.5. You can use the blue slider below, or you can use these arrows. So we want to get to 0.5. Oh, wow, that looks a lot lazier than it did when the frequency was higher. It then tells you to count the number of times the oscillator, this rotator, completes a full rotation in 10 seconds. You're then going to record it. So you have to do 2 things at once. First, you could set a 10-second timer on your phone, since I'm not there to make you park them. So you could set a 10-second timer on your phone, or we have it here in the lower right-hand corner. When you click the play button, it'll start the stopwatch so that you can see when it's 10 seconds, then you can stop counting. Easiest way to count the number of rotations is you see that dark gray circle on the bottom of the oscillator. That tells you when it's what point in its rotation it's at. I like to pick 1 point and then over the 10 seconds count how many times it moves. I'm going to pick when it's at the bottom. And once I see that it reaches the bottom of the cycle, I'll click the timer and start counting. So you can watch. All right. Start the timer. 1, 2, 3. Look at the clock. 4, 5. Okay, I got to 10 seconds. And I noticed that it went around 5 times. So I would record 5 where it says number of waves completed in 10 seconds. 5. We then want to divide that number by 10 to calculate the number of waves in 1 second. Because if we just had 1 second and seeing the way, it's a lot of work. That's why we just picked 10. It's a nice number. Then divide that by 10 to get the number. So if I said that over 0.5 seconds, over a 0.5 frequency happened 10 times, 10 divided by, I didn't say 10. Why aren't you guys yelling at me? Hopefully you're yelling at the screen. So a 0.5, we said it happened 5 times over 10 seconds. 5 divided by 10 is 0.5. So we had 0.5 waves, half a wave, occur every second. All right, you're going to repeat that process, changing the frequency to 1, 1.5, and 2. Pick a point on the oscillation, the cycle, and then count how many times it goes down and around in 10 seconds. You'll kind of be able to figure out the rhythm since it has a smooth flow. All right, go ahead and pause the video, complete part 1, and then start the video again when you're ready for part 2. Did you finish part 1? I hope you finished part 1. Did you finish the analysis on part 1? You did? Great. So let's keep moving on. So now we're going to talk about part 2. Part 2, we're going to look at the relationship between frequency and wavelength. We're going to keep all of this set up the same, except now it says to set the simulator to a frequency of 1. You ended the simulation in part 1 at a frequency of 2. So now you're going to decrease it to a frequency of 1. There we go. All right. It then says, let the simulation run for about 2 seconds. Just let it kind of go. Do its thing. We're going to want to measure the wavelength. So we're going to want to see at least one complete wave. It doesn't really matter where you stop the oscillator in its cycle. It doesn't really matter. I personally just like to stop it when it is at the highest point, or the close to the highest point. I really don't see one nice complete wave, so I'm going to let it play a little bit more. Okay, here we go. So now I see one complete wave. It's not perfectly level, and don't worry about the difference between the red and green spheres. It means absolutely nothing for what we're doing. I have the lowest point of my wave, and then the next lowest point is right around here. So it says, using the ruler, measure the wavelength. My wavelength may be different than yours. It all depends where you stopped it in the cycle. But how does this happen? Well, you can move the ruler, you can move it around. You will set it so the 0, let's make that go away. We don't need that right now. So the 0 mark on the ruler lines up with my lowest point. And then I am looking over to the next lowest point. Again, maybe you're going top to top. Maybe you're going from rest point to rest point. It all depends how you're measuring your wave. My wave in this part of the simulation, you can see is about 6.2-ish centimeters. So I would record 6.2 centimeters under a frequency of 1. You're going to go through. You are going to change the frequencies. Again, let it run for a couple seconds, do its thing, find a nice complete wave, and then you are going to measure the wavelength. So I'll just show you quickly. When you get a little higher, we'll just do a random number, and you play it, we know they're much closer together. So move that ruler to measure your wavelength. Like I want to go from here to here. Don't keep it at the lowest, just the point that you're starting at. You want to keep moving that ruler to where you're going to be measuring your wavelength. All right, go ahead, finish up the 4 other frequencies, answer the analysis questions, and then on the next page, you have a data analysis where you're looking at the relationship between wavelength and the period of a wave. Just to give you some background, a period of a wave is the time for a particle on a medium, for a particle of a medium to make one complete vibrational cycle. What does that mean? Basically, is the time it takes for the cycle to complete. So the oscillator, that's a period, how long it takes to go around one time. So that's what we're looking at, the relationship between the oscillator moving and wavelength. All right, make sure you have everything you need for the data analysis, and I will see you later. Stop there.